Hello students. Uh, in the previous video, we have seen what is an algorithm and different I mean types of the algorithm that we saw that some algorithms in the searching and the sorting domain, right? So in this video, I will be talking about the growth of the functions. We already have seen the functions in detail in the previous lectures. So why we are interested to find the growth of a function? So in at the end of this video, uh, I will be proving that algorithm, whatever we have the algorithm, basically algorithm is basically nothing but a function, right? So if you can recall the definition from the algorithm, as I mentioned in the previous um, video, that what I said, this is a procedure that takes some input and gives some output. So isn't it same like the function? Like function is y equal to f of x, right? So where x is the input, right, and we call y is the output. So we give some input value to the x, and f is a function that performs some operation on this x and then return the value for the y. So for example, if f of x is equal to, so for example, x square plus 3, and what we did, we provide the value of the x. For example, x is equal to 1, and then we got some values of the f of x. And if x is equal to 2, we got some values of the x. If x is equal to 3, we got some values of x. For example, on f of 3, this function is 3 square, that is 9 plus 3, that is equal to 12. So this is the output that we refer it as y, right? So algorithm is nothing but a function, right? The importance of the functions that we have studied in the previous lecture. So here we can see the complete algorithm is considered to be a function. Now, what is the growth of the functions and why do we need to study the growth of the function? Let's have a look over this. So what happens in both computer science and in mathematics, there are many times when we care about how fast a function grows. Sorry. Obviously, if I have an algorithm in order to sort the data elements, or in order to search the data elements, if I have an algorithm and we are calling it as a function, this is really important to understand that how fast this algorithm grows, how fast the function grows. Definitely the function grows based on the number of the inputs. For example, in order to search an element from the list, let me talk about the linear search. So if the elements are 500, so the maybe it require, I mean, the growth of the function is smaller. But if they are the 500,000 elements, so the it require more time. So in order to understand the time taken by an algorithm, we need to understand that how the function grows. And when we talk about the growth of the function, I mean by the behavior of the function. Whether if I change the number of inputs, parameters, how the function will behave, whether it will behave exponentially, whether it will behave linearly, whether it behave, I mean, whatever is the behavior of the function, that I need to understand, right? So in computer science, we want to understand how quickly an algorithm can solve problem as the size of the input grows. This is really important. This is really, really important. That actually decides the algorithm. As I mentioned in the previous video, we have more than 200 sorting algorithms. So which one is better? Who will decide? This growth of function will decide. If the number of input grows, how will be the how the algorithm will grow, and how quickly the algorithm can solve that problem, right? So what we do, we compare efficiency of two different algorithms for solving the same problem, right? So we can determine whether it is practical to solve, to use a particular algorithm as the input grows, right? So in this video we will understand how how we can determine the growth of the function. And in the preceding video, or maybe at the end of this video, I will be talking about the complexity of the algorithm that actually depends on the growth of this function. Clear? So in order to determine the growth of the function, we usually understand the asymptotic notations, right? So we actually learn about the asymptotic notation. asymptotic notations. So what do we mean by the asymptotic notation and why do we call it the asymptote? So asymptotic notation is when the number of input, for example, n approaches to infinity. We always talk about the large number of the inputs, and there are three asymptotic notations that we will study here. That is, one is called big O, another is called big omega, and the third one is called big theta. So we'll see one by one all these three asymptotic notations. Why do we call it the asymptotic notation? As if you can recall what is an asymptote. Asymptote, if you okay, and let me give you the one example. If you can see, if you can guess what is the, I mean, this graph. This graph, so for example, this is the graph of what? This is the graph of, I mean, this is the rough diagram. So this is sine x, isn't it? Right? If I draw another graph, so for example, this one, right? This is what? This is cos of x, right? And if I ask you to draw the tangent graph of the tangent of x, what is tangent of x? Tangent of x is what? Sine x divided by cos x, right? And if you draw the graph, this graph is like something like this, right? And for some value it becomes infinite. This is going to infinite side, this is going to infinite side. So the value where it, this whole becomes zero, I mean, if cos x is equal to 0 divided by something is undefined, those points are called asymptotes, where the values become 0, moving towards the infinite value. So tending towards the infinite, as I already mentioned, we are interested to find the values when it tends to the infinite. Number of input tends to the infinite value, right? So we have three notations: big O, big omega, and big theta. We see what are those values. So first of all, let me discuss about the big O notation. So for example, if we have a function f and g be the two functions, right? F function and x g function, from the set of integers or the set of real numbers to the set of real numbers. So f and g are the functions such that f is basically mapping from z or r to the real number. G is also the mapping from z or r to the real number, right? Then we can say that f of x is order of g of x, or big O of g of x. When we can say that the f of x is big O of gx, if there are constants c and k such that the absolute value of fx is always less than or equal to the g of x multiplied with some constant value, right? So it's say, for example, if we have some function fx, the function f of x, right? And we have another function g of x, right? And if we can find the absolute values, obviously we will be talking about the absolute values, means the positive values, right? We always talk about the positive values in terms of the growth of the function. We'll see why. And if we can find we can if we can form the inequality, right, less than or greater to, such that if we multiply this g of x with some constant c, and this inequality satisfies, right? Then we call this f of x is big O of g of x, right? Or in other ways, we call g asymptotically dominates the f, right? G asymptotically dominates the f's, right? And for that, there are some conditions. Some condition is this c should be greater than 0, right? And then there is another constant x k, right? Another constant k that is always less than x, right? Or other words, x is greater than k, right? Some constant value k. So what does it means? It means we have a function fx, we have a function gx, two functions are there, and we say that f of x is as I mean less than or equal to the g of x with some constant after some k values. Let's see the graph of this and then we can understand. So for example, this is the graph of the g of x, right? This is the graph of the g of x, and this is the graph of the f of x. You can see this one is the f of x, this one is f of x, right? F of x. And For this g of x, if I can multiply it with some constant value cgx, and if if this is greater than this, this fx is always less than this cgx, then we call this f of x is big O of g of x, right? After some value of k, such that this k is x is always greater than k. You can see before this point, we this region is in this region, this f of x may go up of the c of gx or may go beyond the c of gx. We do not care about this. We do not care about this region. This region does not matter. After this k value, all the values of x will return such that f of x is less than or equal to c of g of x. If we can hold this property, we call f of x is g of x. And there are several ways to solve this problem. So for example, let me just say we can solve one equation here. So for example, f of x is equal to, for example, 3 x 3x, let's say for example, just yeah, f of x is equal to 3x plus 2, for example, and I am saying g of x is equal to n, and I want to check whether this f of x is big O of g of x or not. Remember one more terminology, that we say that this c of g of x is upper bound of f of x, right? We say that this is the upper bound of f of x. That means f of x will never cross this g of x. G of x remains the upper bound of this f of x. That's why f of x is always less than or equal to c of g of x. Clear? So if I want to find this, check that whether this f of x is uh, f of x is order of g of x or not, big O of g of x or not. So let's say for example, what I can do is, I know that if based on this inequality, what I can say is 3 of 3x plus 2 is less than or equal to n, right? That is gx, right? Based on the inequality that we have formed in the previous slide, right? 3x plus 2 is less, okay, let me call it x as well. G of x is x, right? X, in order to make the same variable. 3x plus 2 is less than or equal to x. Clear? So then how we can see that, can I find some value for that this value this inequality becomes true. So since I know that this 2 is since I know that this 2 is, yeah, so let me write it in a other way. Let me just erase it, because what we are going to do is we are going to formulate the inequality, and for the inequality we need to check the values. So let's say how I'm going to find the inequality. So I need to the given function is 3x plus 2, and I want to check whether it is the big O of x, g of x or not. So the equality says 3x plus 2 should be less than or equal to, remember the definition, right, from the previous slide, right? So 3x plus 2 should be less than to some side of this one. So let me write it again here. 3x plus 2, for example, just to give you one example. So what I am going to formulate a relationship. So uh, is this relationship holds? So what I am going to do is I need to make this term greater, right? I need to make this they make this term greater, right? 3x plus 2, I need to make this term greater. So how can I upgrade this terminology so that this can become greater, right? So for example, if this is 2, I mean 2 3 4 5 6 7 8 up to n or up to x value. So that does not matter if I write something like this: 3x plus 2 less than or equal to 3x plus x. So it doesn't matter any variable, right? Any value of the from this one. So this, we can simplify this one like 3x plus 2 less than or equal to what? 4x. isn't it? Right? So we can see that we can okay, if I plot the graph of this one, we already know how to plot the graph of the function in the previous lectures, right? This is the x value, this is the y value. So if I substitute x 3x plus 1 less than or equal to 4x, so if I take the x is equal to 1, what will happen? This will happen 3 plus 2, that is 5. Okay, so this will become 5 and this will become 4, right? So 5 is less than 4. 5, no, it is not true, right? Okay, then that means this inequality is not true, right? For what value? For 1 is it is not true. I will find the next value, that is 2. If I substitute 2 here, this will become 6 plus 2, that is 8, less than equal to 4 into 2, 8. So this holds. Why? Because 8 equal to 8. For the next value, if it is 3, this will become 9 plus 2, 11. This will become 12, right? 11 is already less than 12. So that means this inequality is true when some value k is greater than 1. For 1 it is not true. If I take 1, this is not true. If I take value greater than 1, all the possible values greater than 1 is true, right? And then here if you see, this is a c value, right? C value is now 4. C value is 4. You can simply plot this graph here, right? So if I call it g of x, g of x is x, that means 4x, 4 is c, x is already g of x, and if I rewrite it, that this is fx, f of x, that is 3x plus 2, is less than or equal to 4 of g of x, right? Isn't it? For all k values that is greater than 1. So if this inequality holds at k is greater than 1, I can simply say that f of x belongs to order of g of x at c is equal to 4 and k is equal to 1, right? We'll see some more examples in the coming slides, but this is how, if we have one function f of x, we can always say that this is the bond by g of x. G of x is the upper bound when, if this inequality holds. What is that inequality? That inequality is f of x is, oh come on, just 1 minute, let me erase this. That inequality is if f of x is less than or equal to c of g of x for some k that is greater than x. Sorry, for some k that is less than x. So x is greater than k. Clear? Is that clear? So for that, if this inequality is true, we say that the function fx is big O of g of x. So in if one pair of witness is found, what do we mean by here is, let me come back here. This is read by this. The constant c and k that we have just found, c and k, are called witnesses to the relationship f of x is order of g of x, big O of g of x, right? So this pair c and k are called the witness pair, where both are the positive integers. C and k are the positive integers, such that c is greater than 0 and k is greater than x is greater than k, right? If one pair of witness is found, then there are infinitely many pairs, and you can see that from this example. So you can put k is equal to 2, k is equal to 3, k is equal to 4 in this relationship, in this inequality, and you can find out, right? So we can always make the k or the c larger and still maintain the inequality that I mentioned. So you can make the c values larger and the k values larger, and you can maintain the inequality. Any pair c prime and k prime where c is less than c prime and k is less than k prime is also a pair of witness, since you can obviously see that f of x is less than or equal to c of gx, and then definitely c of gx is less than c prime of g of x for k is less than k prime. If this is true, obviously this is another witness pair, right? Okay, you may see that f of x equal to order of g of x instead of f of x is order of g of s. But then this is the abuse of the equal sign, since the meaning is that there is an inequality relating the values of f and g for sufficiently large values of x. It is okay to write f of x belongs to order of g of x, or we can call f of x is order of g of x instead of f of x is equal to order of g of x, because big O of g of x represents the set of functions that are big O of g of x. Usually we will drop the absolute value sign, since we will always deal with functions that take a positive values. That's what we say. These are the absolute signs that we represent for the positive values in order to make it a positive. So we use the positive values. So that's why we are going to drop the absolute signs. So here is one example again. So f of x is equal to x square plus 2x plus 1, and show that this is big O of x square. That means this is g of x, right? So you are required to represent this is as in terms of the inequality, right? That means what does that means? You are going to make x square plus 2x plus 1 less than or equal to x square for some particular c values and k value. So you need to find the c value and the k value here, right? How you are going to find the c value and k value? Since we know that x is greater than 1 and we know that x is less than x square, obviously x is less than x square and 1 is less than x square as well. So I'm going to change again, I mean in the similar way, I'm going to write here x square plus 2x plus 1 less than or equal to the same value, x square plus 2x plus 1, right? Oh, come on, plus 1, right? So I need to make this term higher. I need to make this term higher. How we can make this term higher? We know that x is less than x square. So this x is less than x square. I know that this 1 is also less than x square. So I can make it higher. How? X square plus 2x plus 1. I'm going to replace this x and 1 both with x square. So x square plus 2x square plus x square. Why? Because 1 and x both are less than the x square. And then if you simplify this one, this will become x square plus 2x plus 1 is less than or equal to, this is nothing but 2 plus 3 plus 4x square, isn't it? So that means this c value is 4, and now you need to find the k value. How you are going to find the k value? Just substitute some values into the x value and see where this inequality becomes true. After that, this inequality becomes true for all the values. So for example, if I put 1 here, so if I put 1, so this will be 1 square plus 2 plus 1. So 1 plus 2 plus 1 is 4, right? So this is 4, right? This will become 4, and if I substitute 1 as a x here, this will become 4. So for k value, k is equal to 1, this becomes true. If k is 0, let's say k is 0, if I put k is 0, this will become 1. 1 plus 1, this will become 2, and this will become 0. So for k is equal to 0, this is not true, but for k is equal to 1, it is true. For all values of k greater than 1, this will become true, right? So for that, what I am going to say is take the c value 4 and k value 1 as a witness pair, and so that this inequality is true, we say f of x is big O of x square. All right, so the graph is available in the next slide. Alternatively, we can present as x is greater than 2. So we have 2x less than or equal to x square and 1. I mean, just simplify rather than having the 2, just take the x square, just replace this whole 2x square with the x square, and simply again this will become 3x square. The c value will change only and k value will change, but you have the witness pairs for this relationship in either way, right? So here is the graph of this one. So f of x is x square plus 2x plus 1. You can see this is the graph of the x square. X square plus 2x plus, this one is the graph, right? This one is the graph. And this is the graph of the x square. And then this is the graph of the 4x square. And now you see after this point where k is 1, after this point, I'm sorry, this line is not correct. I mean, straightforward. Let me just erase it in order to resolve this confusion. Uh, okay. So for the k value, when k value is this K value is after this one value, I mean K value is 1, you can see this function is always lesser than this x square, that is g of x, right? That's why we say this is big O of x square. Next, both fx, that is this one, and gx, x square, are such that f of x is O of g of x and g of x is O of f of x. I mean, in either ways, this is true, right? This is O of g of x and this is, I mean, fx is O of g of x, big O of g of x, and g of x is also big O of f of x. So you need to prove this inequality as your homework, right? So do it as a practice. So this is true. I mean, yes, you can prove it. So if this is true, that f of x is big O of g of x and g of x is also big O of f of x, we say that two functions are of the same order. The order of the growth of these two functions is same, right? By the way, that's why we call it the growth of the function or the order of growth, that how this function grow based on the as the input value grow. So in order to increase the input value x, what is the if x is 10,000, what will be the how it grows? If x is 1, how it grows? If x is 100,000, how it grows? I mean, as the x value is growing, how the behavior of the function is growing, right? Okay. Uh, okay. So if f of x is big O of g of x and h of x, there is another function h of x is larger than g of x, then for all positive real numbers, we say that f of x is order of g of h as well, big O of g of s. Why? Because g of x is already big O of h of x, then consecutively f of x is big O of h of x as well. Note that f of x is less than or equal to g of x for all x greater than k, and if h of x is greater than g of x, then for all x, then f of x is less than or equal to c of h of x as well. If x is greater than k, hence f of x is O of g of h, as I mentioned just now. For more applications, the goal is to select the function g of x in O of g of x as small as possible. That we'll see. We'll find the g of x as small as possible, the least upper limit. I mean, g of x is the upper limit of fx, but we'll choose the least upper limit, right? One more example. Show that 7x square is big O of x cube, right? So 7x square, I mean, you need to prove the inequality that 7x square is less than or equal to x cube, right? How you are going to prove that? I mean, this is very simple, isn't it? So x is obviously greater than 7. Why? Because okay, how you are going to prove that? So you can see you need to, I mean, this is already greater than this one, right? So you can see x is greater than 7. That means 7x square is less than x cube, right? And c is equal to 1. C is 1 here, and k is equal to 7. So in order to, this is already proven, this value is I mean, greater value than 7x square, but c is 1 here. You can see c of gx, you do not need to have any other value of c of gx. For 1, even it's greater, but k value should be what is the k value? You need to choose the k value, that would be 7. You can see that if, for example, you are going to substitute 1, x is equal to 1, so 7x square will become 1, x square x cube will become 1, right? And if you are going to choose x is equal to 2, then you can see, and I mean, for k is equal to 7, this inequality will hold, right? So for for that, 7x square is the big O of x cube. Remember, the higher order polynomial is always I mean, lower level polynomial is always big O of the higher order polynomial. That is the proven fact that we'll see in the upcoming slide as well. Show that n square is not big O of n, right? So that means what you are going to see, this is g of x, n. So that says n square is less than or equal to n, right? Okay, that is not true basically. So how you can prove that? Suppose there are constant c and k for which n square is less than cn. right? So for example, there is some value c constant. For that, this becomes true. For example, whenever n is greater than k, right? So then if you divide both sides of the inequality by n, this will become if you divide n square divided by c less than or equal to by cn by n, this will become n less than or equal to c, right? And this should be true for all the values n greater than k, and then this is not. This is a contradiction. So if n is not always less than the constant value, that's why this is a contradiction. We say that this is not proven. This n square is not big O of n, right? For the polynomial values, if f of x is some polynomial a n, that is the constant value, right? A n is the coefficient, x to the power of n plus another coefficient x to the power of n minus 1 plus another coefficient a1, a coefficient to the value of x plus some constant value a0. So that's the the polynomial series, right? These are the real numbers, right? Where an is not equal to 0. So then f of x is big O of x of n, right? So this fx is big O of x of n, the first higher order term polynomial, right? This is the proven fact. How you can prove that? So f of x is equal to this one. We need to establish the inequality. I am writing both the same terms on the both sides of the inequality, as we mentioned in the previous slides as well. So now then, if you take the x of n as a common term, so you see an plus, I mean, these are the constant values divided, an minus 1 divided by x, an, I mean, these are the values remaining on both hand sides. But on the other hand side, you will see the x, since it is the xn greater than this value, x is greater than the xn, so that's why this xn value is terminated from that side. So based on choosing some constant value c, that is a and all this series, and on k is equal to 1, we can see that f of x is big O of x of n, since you can prove that this is only x of n and this is only the constant value, and on the left hand side of this inequality we have the xn, and inside this coefficient value we have the x values as well, right? So we can say that f of x is big O of x of n, and remember this as for example, the higher order polynomial is always the big O of that value, right? uh, Here is the example. Use big O notation to estimate the sum of the first n positive integers. So first n positive integers means we are going to find 1 plus 2 plus 3 plus 4 plus up to so on plus n, right? We are going to find the value, we are going to estimate the big O of this one. And since we know that the higher value is the n, right? So since all the values n minus 1, n minus 2, n minus 3 up to 4, 3, 2, 1, they all are smaller than this n. So we can establish the inequality n plus n plus n plus n so on up plus n. That is nothing but this becomes the n square, right? Right, the n square. So that means this is nothing but big O of n square. So 1 plus 2 plus up to n is nothing but n square, where c is equal to 1 and k is equal to 1. You can prove this inequality like we have proven in the previous examples. So it says use, another example is use big O notation to estimate the factorial. So f of n is equal to n factorial. N factorial, the definition of the n factorial is nothing but the multiplication of the first n numbers. So for example, 1 into 2 into 3 into 4 into up to n, right? So what would be the, we need to establish the inequality for that. So 1 into 2 up, this is the inequality, and all the numbers less than n minus 1, n minus 2, they all are less than n. So we can simply establish the inequality n into n into n into up to n. So this is nothing but n to the power of n, right? So that means n factorial is big O of n to the power of n for c is equal to 1 and k is equal to 1. All right. Another example, use the big O notation to estimate log n factorial. Since n factorial is, we already know that less than or equal to n to the power of n. So take the log on both sides. So if we take, okay, so if n factorial is less than or equal to n to the power of n, so take the log on both hand sides. So log of n factorial is less than or equal to, come on, just 1 minute, this is annoying, this pen. sometimes is really creating troubles. By the way, anyways, so this is a less than or equal to log of n to the power of n. And we know the property of the log. So whatever is the power, this will come down. So log of n factorial is less than or equal to n to the n log n, right? So that's condition for c is equal to 1 and k is equal to 1. So that means this is basically log of n factorial is belongs to big of n log n, right? Is that clear? Okay. So this is the graphical representation of the growth of the function. Here you can see if the function is just a constant value, this is the constant function. If it is a log n logarithmic function, a log n means logarithmic function. So logarithmic function grows and then becomes almost as per the constant function. Then this is n is a linear function, right? N log n, you can see this is a higher function. Then n square, then 2 power n, and then n factorial. N factorial is n power n, right? So this is the growth of the function. Means these they're based on this we can see there are different classes of the functions based on the order of the growth. One is the constant class, right? That is the best class. The least, I mean, you can see this is the constant one. Then the logarithmic class, then the linear class, then the linear logarithmic, then the polynomial class, right, to the power of n. Then exponential class to the power I mean the exponent is the variable is on the exponent. Then the factorial class. So the highest category or the highest time taking, the highest order of the growth or of the function is the n factorial, right? So we accept the functions in terms of the algorithm up to, I mean, based, we classify the algorithm based on the order of the growth of those functions. Clear? So here are some useful big O estimates involving logarithmic power and the exponents. So for example, if we have some variables such that d is greater than c and c is greater than 1, right? So that means c is greater than 1 and d is greater than 1 as well. So that means n to the power of c is big O of n to the power of d. As I mentioned earlier, higher order, right? But n to the power of d is not n to the or big O of n to the power of c that I mentioned. We take the higher order always. So if b is greater than 1 and c and d are positive, then then log base b of n to the power of c is always big O of n to the power of d, right? So whatever is the base b and to the power of c, we take it to the order of d. N is n to the power of d, but n to the power of d is not always big O of the log base of log base b of n to the power of c. This is not true. I mean, you can prove this. You can go to the your textbook, see your textbook. There are proofs available for these inequalities, for these order of growth. If b is greater than 1 and d is positive, right, then n to the power of d is big O of b of n. But big b of n, b power n is not big O of n power d. How? Why? Just go and see the textbook. If c is greater than b and b is greater than 1, then b of b power n is big O of c power n, right? But c of n is not. I mean, you need to remember these some useful estimates in order to quickly solve the questions. For proof, please refer to the textbook, right? Combinations of the functions. If we have more functions, we can combine them in order to find the order of the growth. For example, you have f1x, right? And this, that is the big O of g1 of x, and we have another function f2 of x, that is big O of g2x, right? Then if we want to combine these two functions in terms f1 plus f2 of x, then it will be big O of what, g1x or g2 of x. Obviously, which one is the maximum of these two, right? Since big O is the upper bound, the maximum value, so if we combine f1 plus f2, they will be the big O of maximum of g1x and g2x, right? Again, for details, you can refer to the textbook, that why it is, I mean, there's some proofs and examples are given there. If f1x and f2x are both big O of g of x, both f1 and f2, then obviously f1 plus f2 of x is big O of g of x. Then that's the straightforward rule, that these two functions are already big O of gx. If we combine them, even add them up, they will be the big O of g of x. If f1x is big O of g1 of x and f2 of x is big of g2 of x, and we combine them in terms of the relationship f1 f2 of x, then this is big O of multiplication of g1x and g2 of x, right? So this depends how we are going to combine these functions. Clear? So ordering the function by order of growth, as I mentioned earlier in this slide, that we mentioned it constant, then the logarithmic, then the linear logarithmic. So this is the exercise that can you rearrange these functions in terms of the order of growth. So see if there is any constant, so that will be the number one. So for example, fn is 10,000. Obviously, this is the there is no variable involved, so it doesn't matter it is 10,000 or 10,100,000. So this is the constant. The odd this will not grow. This grow in a constant time. So this will be the number one. After the linear, after uh, the constant, we always see the logarithmic function, right? So if there is any log function is for example, is there any log function? This one is the log function, this one is the log function, this is not the log, but this is the linear logarithmic, quadratic logarithmic, by the way, right? So this is one is also the cubic logarithmic function, right? So we'll see how, I mean, these functions are computed. So I'm going to just show you the results. You can evaluate these functions by your own, that which one is the greater, which one is the smaller. So I mentioned you already that this is the constant, this does not grow, this grows slowest because of the log of n, then this grows log n square, then this grows. So just establish the arguments that which function is smaller and which function is greater, and then I mean, this is the correct order, this is the given order. So you can see that how we have rearranged these functions based on this slide. Clear? Okay. Now big omega. So big O was the upper bound, right? Uh, Sorry, big O was the lower bound. Where I mean that's the uh, uh, big O was the lower bound. I mean the function remains lower than the this g of x. So big omega is called the upper bound. Or okay, this is the lower. Sorry, I mean just go. I mean big O was the I'm sorry, big O was the upper bound, right? Always gives the upper bound. Big omega gives the lower bound of the function. So if I plot it on the graph, I'm sorry, again this pen. Okay, so if we draw it in a graph, right? So if this is f of n, right? So for the big O, if this is g of n, c of g of n, right? After some I mean values, this is the f of n. So after this is the upper bound for this f of n, as mentioned in the previous slides. For omega, what happens if this is the graph, and I'm going to say this is f of x, right, or f of n, then there is a function for example, there is a function for that, this becomes the c of g of x, right? That means this function, this is the lower bound of this f of x. This f of x will never come before this g of x, right? That's why we call it the lower bound of f of x. So the definition is let f and g be functions from the set of integers or the set of real numbers to the set of real numbers. We say that f of x is omega of g of x when if there are constant c and k such that f of x becomes greater than c of g of x, right? So f of x is always greater than c of g of x, where x is greater than k. In terms of big O, f of x is always less than or equal to c of g of x. In big omega, f of x is always greater than or equal to c of g of x, right? So big O gives an upper bound on the growth of the function, as I mentioned, while big omega gives the lower bound. So big omega tells us that a function grows at least as fast as another, right? So f of x is big omega of g of x if and only if g of x is big O of f of x, right? So that means if g of x is big O of f of x, then obviously f of x is big omega of g of x. You can see in either ways, right? So this follows from the definition. So for the next slide, so see, let's say for example, we have f of x is 8x cube plus 5x square plus 7, and we want to say that this is omega of g of x, where g of x is x cube, right? So we can always establish the inequality 8x cube, right? 8x cube plus 5x square, this is greater than or equal to x cube. Then we need to find some value for that. This term becomes the lower. So we found that c is equal to 8. We can find this one, and we need to find the k value on which for which this inequality becomes true, right? If this is true, we can say that f of x is big omega of g of x, and consecutively g of x is obviously big O of f of x. All right. And the third terminology that third term that we use is the big theta notation, right? So the theta notation is, let's see, if it's basically the tight bound. Theta is a tight bound between the lower bound and the upper bound, right? So what do I mean by the tight bound? If I draw a graph, so for example, if this is my fx, right, f of x, then this is g of x, right, g of x for some more value of the g of x as well. So we have two function, I mean, not two function actually. We have the g of x, but we have two constant value for c1 and c2. F of x is bound in g of x for two constant values, c of x and g of x, after some k values, right? So that is mentioned here. If f and g be the functions from the set of integers or the set of the real numbers to the set of the real numbers, the function fx is theta of g of x if and only if fx is big O of g of x and fx is big omega of g of x. That means we have, for different constant values c1 and c2, fx is both omega of g of x and big O of g of x, right? We say that f is big theta of g of x, and also that fx is of order of g of x, and also that f of x and g of x are the same order, right? So that means f of x is theta of g of x if and only if there exist constants c1 and c2 and k values such that this f of x is bond is become greater, f of x becomes greater with c1 g of x and becomes smaller to the c2 g of x for some value x greater than k. So this follows from the definition of the big O and big omega as well, right? So the theta is the tight bound, omega is the lower bound, and big O is the upper bound, right, for the growth of the function, right? So some examples are here, show that the sum of the first n positive integer is theta n square. When it becomes a theta, when it becomes a theta, when it is both big O, and omega as well, right? Then only we can call it as a theta notation, use the theta notation. So it says sum of first n number is big theta of n. We already have seen that sum of first number n number is big O of n square in the previous slides. We already know that f of n is big O of n square. Now we need to see whether f of n is big omega of f of n or not. So to show that f of n is big omega of n square, we need a positive constant c such that f of n becomes greater than c of n square for sufficiently large n. So summing only the term greater than n divided by 2, we obtain the inequality. So what does that mean? We need to establish the inequality 1 plus 2 plus 3 plus up to n greater than or equal to the same inequality, right, up to n, right, number from n. So what we are going to call, we are going to take only those number that make it greater than that, right? For example, n divided by 2 plus n divided by 2, so on plus n. And if we solve this inequality, this will become n squared divided by 4. So that means this is nothing but 1 by 4. This is equal to 1 by 4 n is n square, right? 1 by 4 n square. So that means this is c value. If we take c is equal to 1 by 4, this inequality becomes true. All right, for all positive integer n. So if this inequality becomes true, it means this is also the big O of n square. This is also the f of n is also the omega of n square. Hence, this is fn is theta of n square, right? Okay. For two different c values. Here c value was 1, c1 was 1, and here c value is 1 by 4, right? So for these two c values, this becomes theta of n square, right? So one more example, f of x is 3x square plus 8x log x, right? Show that this is theta of x square. So the solution is to show that this is both big O and big omega of x of this x square, right? So you can always prove this inequality. So this is left hand side, 3x square plus 8x log x less than or equal to x square. X square is the gx. So you need to find some c value, that is 11 we have found, and k value, that is 1. So for that you can see that this inequality is true, and this becomes the big O of n square, right? How you can solve this inequality. And then we can see that clearly x square is also, I mean, x square is also clearly the big of this one. So, and we can prove that, I mean, in other words, we can see that 3x square plus 8x log x is also greater than or equal to x square. We can prove that inequality, or either way, I mean, we can do that. So if both are true, right? So we can simply say that this belongs to the theta of x square. There are several examples in the exercise that will be given to you for the homework to prove those inequalities, right? So when fx is theta of g of x, is must also be the case that g of x is theta of the f of x. That is always true, right? Note that f of x is theta of g of x if and only if it is the case that f of x is big O of g of x and g of x is big O of f of x. Only then this becomes the theta of x, right? Sometimes writers are careless and writes as if big O notation has the same meaning as the big theta, but it is the different meaning. But usually in algorithms, we actually write the big theta as the big O notation as well, because big O is the upper bound, big theta is less than the upper bound, but as worst as the big O. That's why we use sometime interchangeably these terminologies, but we should be careful that what is the difference between theta and big O, right? So what we discuss in this video is the order of the growth, and we discuss the three asymptotic notation. One is the big O notation, big omega notation, and big theta notation. And based on these asymptotic notation, when the input values is approaching to the infinity, we actually observe the behavior of the function, right? So that's all about this video. In the next video I will be talking about the complexity of the algorithm based on this for the growth of the function. Okay, take care, bye bye.